Okay, in lesson 8.2, we're going to start exploring a new aspect of the quadratic function, and that's when we add or subtract a constant after that x squared term. So this is the big player today in lesson 8.2, and we're going to talk about what influence that has and how we describe that effect on the parabola. So think about what happens here. We've already explored the value of a. We know that this determines two important things: which direction it opens and how wide or narrow the graph is. But in everything that we did when we just had that ax squared, our vertex stayed at the origin every single time. Okay, so what happens now when we add or subtract a constant to that, when we have a number after it, maybe like this, or maybe like this? What effect does that have? Okay, well, essentially you can think of it, in fact, if we look at this as an example real quick, if we didn't have the 5 there, it would be the parent function. It would just be x squared, right? So when we think about what that does, we're basically saying that essentially in this function, we're going to take those normal outputs of the parent function, which are the perfect squares, but then every single one of those outputs is going to get increased by 5. So every output that was originally maybe at 1 and then 4 and then 9, like we've been doing with the perfect squares, each one of those outputs then gets increased by that 5 because we added 5. So when normally it was 1, then 1 plus 5 would land us at 6. Then 2 squared is 4, but 4 plus 5 would land us at 9. And this would even affect our vertex, because even if this was 0, 0 plus 5 gives us 5. So what we realize is that when we're adding a constant, it basically takes every single point on the original parent here is the middle one, and it increases every single point by that amount in the same direction. Okay? And what that causes is a vertical slide up, or even better yet, the real vocabulary for that is a translation. You probably dealt with a little bit with translations in 6th and 7th grade. So if C is positive, okay, that's all that means, positive, then our graph is simply going to have a vertical translation that many units up. The entire graph just slides. It doesn't affect the size, the shape. It literally just slides it upward, okay, in that many units. So if it was plus 5, this would be basically the parent function, but just translated 5 units up. So every point is going to shift 5 units up. If C is negative, then the exact same thing happens. It's still a vertical translation, but it's that many units downward. So for example, if you look at number 2 here, quickly, notice it's still the parent function. When we're squaring, we're still just doing x squared. That would be all our perfect squares. But then after we get that output or that result, it would subtract or decrease by 3. So every point would move downward that many units if it were negative, and all the points would be affected, including the origin, because 0 minus 3 will land us on negative 3. So then that would be a vertical translation or slide down. And that is the effect that having a constant, right, a number without a variable at the end of our quadratic, that's the impact that it has. It either slides it up that many units or down that many units. It's a very straightforward, pretty comfortable relationship that you're going to see when you graph those. So it's just a vertical translation, slide, translation up that many units or down that many units. And that's all it is, okay? And so we'll practice a few of these. We'll see also what happens, because especially when we slide it down, if it's opening upward, all of a sudden our x-intercepts change, right? Before, our x-intercept was always at the origin, but once we start to slide this around, sometimes we're going to have parabolas that don't intercept the x-axis at all, and sometimes we're going to have parabolas that intercept the x-axis at 2 different places. So we'll lesson about what happens there and how we find those intercepts. And last but not least, we're going to do a few word problems or real life scenario problems that involve free fall. Free fall happens to fit right in with this particular topic. So I do want to make a mention. Please make sure you write the following down, because it's something that is not given, like they're going to expect you to know it. So I'm going to tell you right now. If and when in this lesson you have a few free fall problems, meaning something's dropped from above and it's just free falling, the only thing acting on it is gravity pulling it down, that's called free fall. So for free fall problems, your function is going to be negative 16t to the second plus h, where h is the initial height. So this is, just trust me on this one, they're going to expect you to know it. This has to do with gravity right here. We could get into it more if you want when we get to class, but we'd be expecting, first of all, the object to go down. That's why it's negative. The 16 has to do with the acceleration of gravity, because that's the only thing acting on the object. Time is how long it's been since it's dropped. So the moment you let it go, the timer starts. 1, 1,000, 2, 1,000, 3, 1,000. And this is going to document the height of the object as it is falling. So really the big player here that you need to insert for each of those word problems is h, which is the height the object is dropped from. Okay, so that's your h. Okay, so as long as you can insert that, then you have a function that relates time to the height of the object. But this guy right here, you're just going to need to know it. So when you have free fall questions that tell you, oh, so-and-so dropped their cell phone off of the Golden Gate Bridge, you know, the Golden Gate Bridge is, I don't know, 270 feet above the water. Boom, there's your h value. And then you have your function that you can work from. So we'll do an example like that as well. Okay, but first of all, let's talk a little bit about just graphing it and comparing it. Once again, we're always comparing to that parent function. So we're going to compare the changes to the parent, and we're going to graph it. Okay, so again, once you get good at this, I want you to be able to look at a function and describe the transformations or the changes before you even graph it. Even though we're still going to graph it, I think that will really, if you can do that, then it shows that you have a solid understanding of the concept. Okay, so let's go ahead and graph this. Is an upward opening. How do I know? Because a is positive. In fact, a is a positive 1. Like I said a moment ago, this is pretty much the parent function initially, and then they're adding 5. So g of x is just the parent plus 5. Okay, so I know it's going to open upward, and I'm going to put my x-axis down here for that reason. My y-axis here. So it looks like that. Okay. And then if we should know how to do this now, pretty much like, you know, like our sleep. The parent function is just those perfect squares. So 1 squared is 1, 2 squared is 4, 3 squared is 9. I think that's up here, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, good. And then we just copy it to the other side. And there's our parent parabola once again. Okay, so that's f of x. Okay, and then we're going to go ahead and graph g of x. Well, g of x is x squared plus 5. So if I do 0 squared is 0, but plus 5, that moves that vertex up 1, 2, 3, 4, 5 units. 1 squared, well, 1 squared is 1 plus 5 is 6. So that would take us up to 1, 6. 1, 2, 3, 4, 5, 6. There it is, and I copy it over. And then if I do 2 squared, well, 2 squared is 4. 4 plus 5 is 9. So if I go, if I go over 2, I would have to go all the way up to 9. And so there is our parabola. And notice the width is the same as the parent. Everything is the same. The only difference is that every point has been shifted 5 units up. Every point has been shifted 5 units up. And there was no other change, right? There was no a value that was different, so there was no reflection. I don't expect there to be a change in a stretch or a compression because their a value didn't change at all. It was just this guy right here. And you can confirm that. You can grab your calculator. Make sure we're still on the same page here. If we compare the parent function and then that x squared plus 5, and we come up with a graph here. There's our parent, and here is our new one. The width is the same. Everything is the same, and if you compare the values, you realize that this g of x is just always 5 more than the original parent, because that's what that plus 5 does. It just increases your values by 5. So where the original output was 1, then it's 6. 4, then it's 9. 9, then it was 14. Then 16 went to 21, because it always increased by 5 after we squared. Okay, so that causes, to finish this out and describe this, the only transformation or change compared to the parent here would be a vertical translation, which is the same as a slide or a shift, by 5 units, or translation up, I should say. I should be specific here. So that would be a vertical translation up 5 units. Okay. Let's say the word units here. Okay. Let's try one more. This is our parent right here, right? Very similar. Our a value didn't change, so I'm not expecting a reflection or a vertical stretch or shrink, but they did subtract 3. So that means that every output that normally would happen in our parent is then going to be decreased by 3 units. So like we said here, we're going to expect a translation or a shift that many units down. Okay, so if we graph this, I am going to allow myself a little bit of space here now, since I know that this is going to slide down on me. When I graph it, okay, so, and again, our parent is at 1, and then at 4, and then it would go up to 9, but I don't have enough room, and that's okay. So, and then at the vertex. So here's our parent once again. That's our f of x. Oh, I didn't label my g of x over here. All right, let's label that. And then the new one, again, you could do it on a calculator if you like, or you could think about just those same outputs, but minus 3. So whether you plot them this way and you just plot your points, when you are at -1, we're going to be at -2. At 0, we're going to be at -3. At 1, we're going to be back to -2. We already knew that. At 2, we're going to be at 1. And let's see, at 3, we're going to be at 6. So 3, 1, 2, 3, 4, 5, 6. And so it's really the same parabola. It just slid down. So when you start to introduce that c value, this is our g of x, the vertex is no longer always at the origin. And we would describe this as a vertical translation three units down. Okay, and so far that's the only change that occurred there. So there you go. Everything just got, every point slid down the same distance. And that's what that causes. Adding or subtracting a number, a constant really, by itself back here, it causes that vertical slide either up or down. That's it. Okay. So what if we combine that with what we learned in the first half, right? So let's take a look at number 3. This is pretty good. There's more going on here. So when we compare this, again, just to remind you, f of x is what we're comparing to, which is our parent function here. And you should be able to tell what's going to happen here before it happens. I keep saying that, right? As soon as I see this, the moment I see an A value here other than 1, I know that this is going to cause some changes. So let's talk about what that causes. The negative is going to cause it to reflect. That's for sure. The 3 is not in parentheses, but there's a 3 here, so that's going to be a vertical stretch. It's a vertical stretch by a factor of 3. So we expect it to be reflected and look down, go downward. We expect it to be narrower or vertically stretched by a factor of 3. And then that negative 2, like we said, is going to be translated 2 units down because it's negative. So translation 2 units down. Okay, so that is all the things that I expect to happen, and I should be able to look at that and tell before I actually test it. Let's see how accurate that was. We've got our x squared in here, and then for the next line, we're going to go ahead and enter negative 3x squared minus 2. So remember, the negative we said was going to make it reflect and go downward. The 3 we're saying is going to make it look narrower, which is a vertical stretch by 3. And this tells me that the vertex and all other points are going to slide 2 units down. So we expect the vertex to not be at the origin, but be 2 units down from that. So let's graph it and see. There's our parent function, and there's our new function. There it is, downward. The vertex has shifted down 2 units, and the width of it is a little bit less wide or narrower than the original. There it is. And then you can pull up your table of values so you can graph some of those points. Okay, so obviously we need positives and negatives here to graph it. So it might look something like this. Again, when we start off with the parent function, that's at 1 and then at 4. So there's my curve. So that's f of x. And then when I graph these points, I can use my table if that helps, especially this one that has a lot of different transformations. At negative 3, whoop, there's no way I'm going to make that fit. 29, no way, right? But perhaps, no, I'm not even going to make 14. I'm hoping that maybe I can fit negative 1. So negative 1 is at negative 5. So that's negative 1. 1, 2, 3, 4, 5. So there it is. And then I'll copy it to the other side. And then our vertex is at 0, negative 2. So even these 3 points are enough to kind of exemplify what's going on. You don't need a gazillion points. Okay, it really is enough there to show us, oh yeah, this looks different, right? And then last but not least, let's actually verbally describe it. I kind of already described it there, but that's a mess. I really would want you to write it. I would want you to say that n of x is reflected across the x-axis. Okay, comma, and then it is a vertical stretch by 3 and translate it let's see, 2 units down. Okay, so I've got my reflection across the x-axis, the vertical stretch by a factor of 3, and then translated 2 units downward. That would complete all of the different transformations or changes that happened from the parent to the original. Okay, try number 4. Go ahead and pause it, give it a shot. Try number 4, and let's see how that went. And then we'll move on. Okay, so check to see how that went. If this is your graph, this is our parent, and the pink one here is q of x, then you're in good shape. So just as expected, it's still positive, so it's still opening upward. That 1/2 does make it wider looking, which is a vertical compression by 1/2, right? And then the -4 just slides everything down. So our vertex is down to -4 here, and all of our points slide down that way. So it's a translation 4 units down as well. So really two big changes here. This was a vertical compression by 1/2 and a translation 4 units down. That's what your graph would look like. Okay, so then let's talk about the zeros, because remember, this is just another fancy word for the x-intercepts. And what happens is when you start moving this up and down, we start getting those x-intercepts change from just being the origin every time to being a couple of values, sometimes no values at all. Like this one doesn't have any x-intercepts, but this one has 2. So remember, this is going to connect to what we had been doing in Unit 7 to find those zeros, which is really just the x-intercepts. Okay. That's just a fancy, we also call them the roots. Remember, we can do a couple of things. In this particular style of equation where it's just the x squared term and the constant, one of the things that we can do is solve for x, right? So what's option 1 is just solve for x. So if I wanted to get x alone here, first we always set it equal to 0, right? Because that's our zeros. So I would set it equal to 0, and then I would get x by itself, right? So maybe I would move this x term to the left so that it's not with the 1. And then we would get x squared is equal to just 1. And then to get rid of the power, don't forget, anytime you want to get rid of an exponent, we just take that root. So then we would take the square root. And here's a biggie, right? When we take the square root, we get x by itself. But on the other side, we get the square root of 1, which is both positive and -1. We have 2 intercepts here. If you only write 1, you're leaving off an entire solution or root or 0 here. Okay. Basically, parabolas are going to have either no x-intercepts or 1 if it's at the origin, or I'm sorry, at the vertex, my bad, or it's got 2. So it's got 0, 1, or 2 solutions. This one has 2 solutions. So this is telling me that this graph is going to cross the x-axis at -1 and +1 for this problem here. Okay, so you want to make sure that you have both solutions when you do the root of that number. The other option is to do it exactly how we learned in Unit 7. So again, we would set this equal to 0, and then we would factor. So our GCF here, I know that I see that I have a 4 that goes in, and whenever the leading coefficient will a negative as well. So I have a GCF of -4 that I can pull here. And when I factor in -4, I get x squared, and then 16 divided by -4 is just -4. And then I realize, oh, that's a difference of squares right there. So I can factor that further. So I get -4, and then this factors to x plus 2 and x minus 2. And then we use a zero product property. The only way that this times this times this can be 0 is if any one of those is 0. So I'll set each one equal to 0. Well, the -4 is never going to be 0, so I don't have to worry about that. But I would set the x plus 2 equal to 0, and I would set that x minus 2 equal to 0, and we would solve with the zero product property. So one of our intercepts would be at -2 here, and the other one would be at +2. Again, 2 intercepts, right? So it makes sense. Whether you write them separated out like this is fine, or you do the plus minus. But if you only write one sign and that had 2 intercepts, then you only have half the answer. So you want to be careful with that. Okay, so you've got 2 options, but this starts to become a thing, right? Because we now have parabolas that hit that axis more than once. So finding those x-intercepts becomes important. All right, let's try one of these. This is really about sketching anything that has these characteristics. So there might be more than one answer that works. Let's try number 9. It tells you they want you to sketch a parabola that meets all of these characteristics or these criteria. They tell us that the parabola opens downward and it has a vertex at 0, 5. So as long as you can meet that criteria, you should be all set. So the big thing here is it doesn't have to be a perfect or amazing. You just want to meet the criteria here. So if it tells me that the vertex is at 0, 5, then that's where I'm going to put my vertex. 1, 2, 3, 4, 5. There's 0, 5. And then it opens downwards. So then I would just make a parabola that goes down, and you're set. Okay? So that's just, and again, there's other possibilities, but as long as it opens downward and that's your vertex, you're set. Okay? All right, let's flip it over and let's finish out with that free fall problem that I promised you, and then we'll end here. So it tells you here the function, and this time they were nice and they gave us the function, but sometimes they just expect you to remember it or know it. So that's why I wanted to make sure we had it at the front of our notes. It tells you the function of f of t is negative 16t squared plus s of o, or s of 0. And that represents the approximate height of a falling object t seconds after it has been dropped from that initial height, right? That's always your initial height that you're adding there on the end. A tennis ball falls from a height of 400 feet. So immediately I know that's going to be my 400 right there. Okay, how many seconds until it hits the ground? So first of all, let's come up with the function. The function is going to be this guy again, but we're going to insert that initial height. So the ball is still being acted upon by gravity. Time is still time, but our initial height that it was dropped from was 400 feet. So this is the version of this equation that we need for this tennis ball problem. And then they want to know after how many seconds, so that means we're looking for a value of t, does it hit the ground? Well, once it hits the ground, then my height is then at 0. So if I start at 400 feet, that's my initial height, and it's dropping. When I'm at the ground, then the height at that point is just 0. I'm at the ground now. There's 0 height. So that means that I want to set this equal to 0, because this is what represents the height. So I would set this equal to 0 and solve this function just like we practiced a moment ago. Okay, so if I look for a GCF, I am going to realize there is a GCF here. 16, let's make sure, 16 does go into 425 times. So I'm going to factor out a negative 16 here. That's going to leave me with t squared minus 25 when I divide that out. And then I want to recognize, oh, but that's a difference of squares. And so we're going to factor that further. T plus 5 and t minus 5. There's our GCF, and all of this is equal to 0. And then we'll just use the 0 product property. The only way this can be 0 is if this or this or this is 0. Well, that's never going to be it, but these guys might. So let's set those t values equal to 0. So one option is that t plus 5 is equal to 0, and the other option is t minus 5 being equal to 0. Well, if we solve here, we're going to get a negative time, and I don't know about you, but I don't think that it's possible. We haven't learned how to time travel yet. There is no negative time, so that's out. But if we solve this, add 5, tells me that this is going to happen after t equals 5, or 5 seconds. So how many seconds does a tennis ball hit the ground? The tennis ball hits the ground after 5 seconds. Okay. What about this one? It says, suppose the initial height is decreased by 384 feet. So decreased by that much. So that initial height, that 400, is decreased by 384 feet. So that leaves us at 16 feet. How many seconds does the ball, and after how many seconds will the ball hit now? So now we got to use this new height. So if we take that original function, but we decrease the initial height by 384, then our initial height becomes just 16. And really then we can just practice this again, right? Again, they want to know when does it hit the ground, so we would set it equal to 0. We would look for a GCF, which in this case is negative 16. That leaves us with t squared, and then positive 16 divided by negative 16 is just a negative 1. We recognize this is a difference of squares, indeed. So that factors to t plus 1 and t minus 1. And then we use a 0 product property. So we'll set each one of these equal to 0. t plus 1 equals 0, t minus 1 equals 0, and we'll solve. So one option is at -1, which again, time travel hasn't been happened yet. We can't really go negative or back in time. But t equals 1 is very doable. So we're looking at 1 second to reach the ground. So it takes 1 second for the ball to hit the ground if it had been dropped from 16 feet. Okay, that's what changes is that initial. All right, and then we're going to leave these guys, although you should be able to graph this because it's really just going to be the original and then shifted, but we're going to do those in class together and make sure that we can do it with while you can ask any questions.